Hello, hello, hello. Hello everyone. Today we shall discuss about the potential energy of a spring. We'll find the potential energy of a spring. You see here how we are finding the potential energy of a spring. In the previous lesson, we have found that the spring force is an example of a variable force which is conservative. So you'll find here that we have a block attached to a spring and resting on a smooth horizontal surface. So today we are explaining this potential energy of a spring in detail. Now just see how we will explain the potential energy of a spring. Hello? Now see, now we'll share this one and you how we how we explain this potential energy of a spring. So we are sharing to you something. You see here, this is the potential energy of a spring in detail. In detail we are explaining, so it will take some time. So um, you see how we are going to explain this potential energy of a spring. So first of all, we'll take this one. We'll take this background. After that, you see how we are going to discuss these things. So we are taking a white color and you see how it is coding for. So today we will discuss the potential energy of a spring. So our explanation is the potential energy of a spring. So here you see, today we are explaining the potential energy of a spring. The potential energy, the potential energy, the potential energy of a spring. Today I discuss with you here in detail. What is that? Actually, in the previous section, what we find, the spring force is an example of a variable force which is conservative. The spring force, the spring force, the spring force is an example, in the spring force an example of a variable force, example of a variable force which is conservative, and we've also found what are the various characteristics of a conservative force. So here I am going to give you three figures so that you can understand what is given here. Suppose this is I am drawing a block of wood and this is A position. This is a spring, suppose, and there is a block of wood here, and this you consider at this middle at x equal to 0, at x is equal to 0. Now you see this is the spring that is in equilibrium position. The spring is now in equilibrium position at x equal to 0. And in figure B you will find that in figure B you will find that the spring is in this way. This is the equilibrium position. So the block is here, and there is an extension in the spring. Suppose the spring is like this. So we find if this is the middle position or this is the equilibrium position, we find B, and there is another point, C point, that is C diagram. It is this one, and the block will be in the here. This is the table surface and the block is here, suppose here. In this case the spring is compressed. You see here, the spring is compressed more, right? So what we find that we are going to discuss, right? Here in this case there is a force F is equal to 0, and here you see there is no displacement, and x is equal to 0. And in case B, that there is a displacement. Here you see this is the equilibrium position. Suppose this is the equilibrium position. This is the equilibrium position, that is x equal to 0. This is the equilibrium position, that is x is equal to 0. And this one is the value of x at this position the displacement is x. So here we find that Fs is negative. The restoring force, you can say this as Fs, restoring force is negative, is negative, is negative, and the displacement is in positive direction. X is positive, x is positive in case of B. But in case of C, you see here that there is a force in this direction, restoring force is in this direction. That is what we call as Fx. Fs is positive, Fs is positive, but x is negative. But x is negative, x is negative. So these are the three configurations we get here, and this is the displacement of x in the negative direction. Now it explain all the three positions here, right? So here you see that in the figure shows a block. The figure shows a block. The figure shows a block attached to a spring, attached to a spring, attached to a spring, and resting on a smooth horizontal surface, and resting on a smooth horizontal surface, a smooth horizontal surface, horizontal surface. The other end of the spring is attached to a rigid wall. The other end of the spring is attached to a rigid wall, right? Then find that the spring is light and may be treated as massless. Find the spring is light and may be treated as may be treated as massless. In an ideal spring, the spring force Fs is proportional to x. In an ideal spring, the spring force, or restoring force, the spring force Fs, the spring force is proportional to x, is proportional to x, when x is the displacement, where x is the displacement, of the block from the equilibrium position, The displacement could be either positive or negative. In case B, it is positive. In case C, it is negative. The displacement could be would be either positive or negative. In this case here you see that in case B it is positive displacement and in case C it is negative displacement. The force law for spring is called Hooke's law. The force law for the spring, this force law for the spring is called Hooke's law. Hooke's law and is mathematically stated as Fs spring force is equal to minus kx. The constant k is called the spring constant. The constant k is called the spring constant. Its unit is Newton per meter. Its unit is Newton per meter. The spring is said to be stiff. The spring is said to be stiff. If K is large. And soft if K is small. Suppose that we pull the block outwards as in B. Suppose that is in position B. Suppose that we pull the block outwards as in figure B. If the extension is xm, the work done by the spring force, the work done by the spring force the work done by the spring force you see here the work done by the spring force we find what are the work done by the spring force. You can find here that the work done by the spring force will be Ws is equal to integration 0 to xm 0 to xm fs dx. This is the work done. So if you want to find the work done, Fs equal to, you know that this is equal to minus Fs equal to minus kx. You put the value as k minus kx dx, and it is the in 0 to xm, it is the limit. So here you find that minus k, the k is a constant 0 to xm, and dx x dx. Therefore it will be x square by 2. Therefore get the value minus k x square by 2. The expression may also be obtained by considering the area of the triangle. So here also we are drawing the D figure, how we find the work done. Suppose this is the force in this direction. This is the force for Fs, spring force, and this is the displacement, right? So if the work, if we find a graph in this direction, so the Fs is equal to minus kx, and area here we get here is, this is the area of this part. So the area we get minus area is equal to minus kxm square by 2. When you are taking the x as positive and Fs as negative, then we are getting this value. So what you get here is that the expression may be also this expression, minus k square by 2 x square xm square by 2. This expression may also be obtained by considering the area, of the triangle, as shown in figure, right? Note the work done by the external pulling force F is positive since it overcomes the spring force. Note that the work done by the external pulling force by the external pulling force F is positive since it overcomes the spring force, the spring force So, or you can say in this way. So here you can see that the work done is minus kx squared by 2, and this is the area of this triangle. Now we'll see that the same is true. The same is true. The same is true when the spring is compressed. When the spring is compressed, when the spring is compressed, when the spring is compressed with a displacement, compressed with a displacement, compressed with a displacement x c, and that is less than equal to less than 0. The spring force does work. The spring force does work. W is equal to minus k xc square by 2. Same thing apparently. While the external force F, while the external force F does work plus k xc square by 2, because they are in the positive. Both the external work force and displacement both are in the same direction. If the block is moved from an initial displacement xi, to a final displacement xf, the work done by the spring force, the work done by the spring force Ws is work done by the spring force is equal to minus integration of x initial to x final, and if it is, we know that minus kx dx, therefore we are getting the value minus k xi square by 2. This will be plus and minus k xf square by 2. This is one equation number 1. So get this one. That the work done by the spring depends only on the end points. Thus the work done by the spring force depends only on the endpoints, only on the end points. Specifically, if the block is pulled, if the block is pulled, from xi and allowed to return and allowed to return to xi, then work done minus xi to xi, kx dx. The work done will be here, you see, kxi square by 2 minus kxi square by 2. So the work done in this case is equal to 0. And you know, in a conservative force, the total work done in a closed path is 0. So you can say that the spring force is a conservative force. The work done, here you find the work done by the spring force, work done by the spring force in a cyclic process, is 0. We know that. So if the work done is in a cyclic process is 0, we can say that force is a conservative force, right? So here you can write here it as that we have explicitly demonstrated that the spring force I initial is position dependent, only as first stated by Hooke, that is Fs spring force minus kx. Number 2, does work which only depends on initial and final position. So here also you see, here we see that work done depends only on initial and final position. Initial and final position. Thus we can say that the spring force is a conservative force. Thus we can say that spring force is a conservative. Spring force is a conservative force. Is a conservative force. The two important characteristics of conservative force is that it depends on your initial and final position. It is independent of path. The total work done and closed path is 0. Now we define the potential energy. Now we define the potential energy of the spring. We define the potential energy we define the potential energy Vx of the spring to be 0. Vx of the spring to be 0 when block and spring system is in the equilibrium position. When block and spring system is in the equilibrium position, equilibrium position. We are defining this one. For an extension or compression, for an extension or compression, extension or compression, x the above analysis suggests that Vx potential energy is equal to kx square by 2. Kx square by 2, that is the potential energy. We may easily verify that. We may easily verify that verify that minus dv dx is equal to minus kx. The spring force, if the block of mass m now we will find a different thing. So if the block of mass m, if the block of mass is a block of mass m is extended to xm and released from the rest and released from the rest, then its total mechanical energy at any arbitrary point arbitrary point x, where x lies between minus xm and plus xm, will be given by half k x m square is equal to half k x square plus half m v square, where we have invoked the conservation of mechanical energy, where we have invoked the conservation of mechanical energy. This suggests that the speed that the speed and the kinetic energy will be maximum at the equilibrium position. The kinetic energy maximum at the equilibrium position x equal to 0. That is half m v max square is equal to half k x m square, where Bm is the maximum speed, where Bm is the maximum speed, or we can write, or V maximum velocity can be written in this way, that root over k by m into xm. Note that k by m has a dimension of t square. Note that k by m has the dimension of t square, and our equation is dimensionally correct, and our equation is dimensionally correct. Dimensionally correct. Dimensionally correct. The kinetic energy the kinetic energy the kinetic energy the kinetic energy gets converted to potential energy and vice versa however total mechanical energy remains constant. This can be depicted graphically below. You see how we are doing this one. Suppose this is the displacement, this is the equilibrium position, this is x max xm in positive direction, and this is minus xm in negative direction. You see here that this is the total energy and this is the energy graph in y direction, capital E, or energy in y direction. So what you find that minus xm to xm, the kinetic energy is maximum at equilibrium position. So this is the equilibrium position, x equal to 0. So the kinetic energy will be 0 at the maximum displacement, kinetic energy, and it is maximum here, right? So we got the graph in this way. So you can find the maximum energy is here. This is the kinetic energy. Here you see the kinetic energy is maximum at equilibrium position, and this is the total energy. How you got the total energy? That if we find the potential energy like this, the reverse of that in this way, suppose this end and this end, the potential energy will be like this. What it depicts? It depicts that at this is the potential energy. Potential energy is maximum at the end, and at equilibrium the potential energy is zero. So do this graph, and the total mechanical energy will be total mechanical energy is equal to kinetic energy plus potential energy. Kinetic energy plus potential energy. So what we get? Parabolic plots. So this figure, suppose 1.1, figure 1.1 parabolic plots. You see, this is parabola. Parabolic plots of the potential energy of the parabolic plots of the potential energy V and kinetic energy K of a block attached to a spring obeying Hooke's law. The two plots are complementary. The two blocks are complementary, one decreasing as the other increases. One decreases as the other increases. The total mechanical energy, the total mechanical energy that is E is equal to kinetic plus potential remains constant. So we have defined all the things in the potential energy of a spring. So thank you everybody for watching this video.